The phases of operation for an inductor in a DC circuit are the storage phase. That's when the inductor is storing energy. The steady state condition, that's after we finish the storage phase and we allow the circuit to continue in its steady state with nothing changing. And then there's the release phase, when we release that energy back into the circuit. So we're going to focus on the storage phase, and I'm going to describe a little bit about what's going on. When we close this switch, what's going to happen is immediately this voltage source is going to try to establish current in the circuit. However, remember what's going on with this inductor is once there's current and that current starts flowing through the coil, it creates this growing magnetic field around the coil. And that growing magnetic field actually creates what we call a back EMF, or back electromotive force, that pushes back against the source. Okay, so imagine it kind of like a voltage source pushing current in the opposite direction. And what that's doing is it's trying to keep the current from changing. It's trying to keep the current from changing through that inductor. Wants to keep current the same, much like the capacitor wants to keep the voltage the same. The inductor wants to keep the current the same. So as it starts, that inductor pushes back against the current and tries to keep the current from being established. Now, eventually, as more and more current goes through the inductor, the magnetic field stops growing, and at that point, it stops pushing back against the source, and then all of the current is allowed to flow through the inductor. Okay, so what that looks like at t equals 0, so right at the point where we close the switch. So what I mean by t equals 0 is we close the switch and we start counting 0, 1. By the time we start counting 1, all of this is changing. However, right at that moment where we close the switch, basically our inductor is acting like an open circuit. It doesn't want to allow the current to change, and the current before this point was 0. There was no current. So right at t equals 0, the switch is closed. Our inductor looks like an open circuit. Once we push past and get to the point where we're allowing all of the current to flow through the circuit, and we call that steady state, at that point, our inductor looks like a short circuit, where all of our current flows through the inductor in this case. Okay, so just as we looked at for the capacitor, we have curves that explain to us kind of what's going on. And if you'll recall, I told you that when we have a value that starts at 0 and then quickly rises to a maximum value, that equation is 1 minus e to the minus x, which in this case is 1 minus t over tau. And then when we have a property that starts at its maximum and drops down very quickly to 0, the equation for that is e to the minus x, or again, e to the minus t over tau. So the same thing will apply to our inductor. So let's look at what's going on from the time we close the switch, t equals 0, to the steady state. Okay, let's first look at the current through the inductor. So I sub L is the inductor current. At this point, at t equals 0, that inductor current is 0. And once we reach steady state, IL becomes I sub S, which is the maximum current that we're going to see. So I sub L has this shape here, where we start at 0 and we go to that maximum current over time. If you remember from our capacitor discussion, the voltage is what did this with the capacitor. The voltage started at 0 and went to a maximum. For the inductor, it's the current that starts at 0 and goes to a maximum. What about the voltage drop across the inductor? Well, for here, that's going to be E, because we have an open circuit here, which really just means that that resistor has no voltage drop since there's no current through it. So across the inductor, we're really just looking at our supply voltage. And after we reach steady state, V sub L would be right here, and that's a short circuit, so V sub L would be 0 at that point. So here is our V sub L, where we start at that maximum voltage and quickly go to 0 there. And then the voltage drop across our resistor, in this case R1. Again, there's no current through the resistor here, so VR would have to be 0. And in steady state, all of the currents flowing through the circuit. So VR is at a maximum here, which in this case is going to be I sub S times R, or since there's only one resistor here, it's just going to be E. So again, V sub R starting at 0, going to a maximum value. Again, remember that the voltage across the resistor and the current through the resistor, I know it's I sub L, but in this case, it's actually in series with the resistor, so I sub L is equal to IR. So notice that they have the same shape because they're related by Ohm's law. There's just a constant that's a difference there. And then the voltage across the inductor is actually what goes to 0 over time. Okay, so we're going to write our equations, and the next thing I need to share with you is how to calculate tau for an inductor circuit. And the way we'll do that is we divide the inductance by the resistance, or the effective resistance of the circuit. So the inductor value in the problem shown above is 4 henries, and we have 2 kiloohms of resistance. So that means we have 2 milliseconds as our tau in this case. Be very careful that you're not using the equation for capacitive time constant, because remember that was our time C. For the inductor, we're dividing L by the resistance. Okay, so let's write our equations. So for I sub L as a factor of time, remember the shape, I'm going to go up here, the shape is the one that starts at 0 and goes to a maximum value. So that's going to be 1 minus e to the minus t over tau, which we just found was 2 milliseconds. And the maximum value that we're going to put there, if you look in this case, when we have 50 volts as our source and 2 kiloohms of resistance, and the inductor looks like a short circuit, then our current is just going to be 50 divided by 2K, or 25 milliamps, 1 minus e to the minus t over tau. Let's look at V sub L. So V sub L so we're starting at the maximum voltage we would see across that inductor, and we're going to 0 over time. So that shape is this one here, starting at a maximum and going to 0. So e to the minus t over tau, and remember, tau was 2 milliseconds. So here we've got, we're going to start at 50 volts and go to 0 over time. So I'll just rewrite that so that they're all kind of lined up. And then V sub R. So notice in my first circuit, circuit 1, we're starting out at V equals 0, and in circuit number 2, VR is going to be at the maximum, which is just E. You could even just say I sub S times R, and the shape, we're starting at 0 and going to a maximum value, and remember that's right here. Okay, so 1 minus e to the minus t over tau. Tau is still 2 milliseconds. So we've got, our 25 milliamps times 2k ohms of resistance, 1 minus e to the minus t over tau, which is just 50 volts, 1 minus e to the minus t over tau. I think I'm going to clean that up just a little bit. Okay, so that's what we see right here. This is I sub L, where you see it starts at 0 and it climbs up very quickly to about 25 milliamps there. And our V sub L, which does the opposite. It starts at 50 volts as that inductor is trying to push back against the voltage source, and then it drops to 0 as it allows more of that current to flow through the circuit. So let's look at another problem and come up with the same equations here. So the storage phase equations for V sub L, I sub L, and V sub R. Okay, so let's look at, first of all, if it helps, I like to look at it as what does the circuit look like when you first close the switch? And then what does it look like when you get to steady state? So when you first close the switch, what we have is the inductor acting like an open circuit because it does not want to allow that current to change. And since there was no current before, it's wanting it to stay that way. Okay. Once it reaches steady state, it's allowing all the current to flow through the circuit. So it looks like a short circuit. So at steady state, your inductor equals a short circuit. Remember, that was the opposite of our capacitor. And you'll find that many things about the inductor are really the complement of what you learned about the capacitor. Okay. So at t equals 0, here is our I sub L. I sub L equals 0. V sub L, which is right here, that's an open circuit voltage. Remember, since there's no current through the resistor, there's no voltage drop either. So we're really just measuring the 40 millivolts across the inductor there. And then the voltage drop across the resistor is going to be IR times R, and in this case IR and IL are the same thing. And if IL is 0, then the voltage across the resistor must be 0 as well. And then at steady state, now that my inductor looks like a short circuit, that's the main idea right there, I sub L is going to be 40 millivolts divided by 20 k ohms of resistance. So we've got 2 microamps there. V sub L, which is right here, now that's a short circuit, and there's no voltage drop across a short circuit, so that's just 0. And then VR will be IR times R, and this time, since IR is IL, in this case, that would mean that our 2 microamps times 20 k ohms of resistance would just be the 40 millivolts. So our storage equations, those are the equations that describe what happens between these 2 points, or rather just this way. Okay, that's where the storage equations come in. So for I sub L, we're looking at something that starts at 0 and climbs to 2 microamps at steady state. Remember, that was this equation, right? Starting at 0, going to a maximum. And that equation looks like 1 minus e to the minus t over tau. So 1 minus e to the minus t over tau, and that maximum it's going to is 2 microamps. Okay, let's back up and find our tau. Okay, so tau in this case is L over R. We've got 250 millihenries divided by 20 k ohms of resistance. So that means our tau is 12.5 microseconds. Now that's not the time it takes to get through the entire storage phase, okay? To get to steady state, we need to take 5 times that to get to steady state. That would be about 62.5 microseconds. Still very fast, but that means that total time here is 62.5 microseconds. That's how long we're in this stage where we're going from the t equals 0 seconds to steady state. It takes 62.5 microseconds to get there. However, that's not what we put in our equation. What we put in our equation is just the time constant, the one time constant. Let's see, I'm going to get rid of more of that. Give myself a little more room here. Okay, let's, so these are my storage equations, remember. Okay, so V sub L is going from 40 millivolts to 0. So that's the other equation. That's the one that starts at 0 and starts at maximum and goes to 0. That's e to the minus x. So e to the minus x, which is t over tau. And that voltage that we're starting at is 40 millivolts. VR, we're starting at 0 and going to a maximum value of 40 millivolts. That's, again, like this equation. So 1 minus e to the minus t over 12.5 microseconds. And the maximum we're going to is 40 millivolts. Okay, let's look at one more example, and maybe we'll plug in and try to find some actual numbers here. Okay, so let's look at the storage equation, storage phase equations for this circuit. So when you have something like this in your circuit, what you can do is you can imagine that's a voltage source to ground. Okay, so if you have 12 volts right here, we're saying we're applying some kind of 12 volts at that part of the circuit. And imagine a ground right there. And you can connect up the grounds in your circuit to make them look like what you're more used to seeing, if that makes you more comfortable. But it really means about the same thing. So I'm going to clear the rest of that out, and let's write our storage equations. Okay, so I sub L, remember, as we close the switch, this inductor is going to push back against the voltage source that's trying to push that current through, and it's going to take some time to establish that current. So the current is going to start at 0 and go to a maximum, which is 1 minus e to the minus t over tau. So we're going to need to find our tau. Let's find that right now. It's L over R, the effective resistance of the circuit as seen by the inductor. So we've got 5 millihenries of inductance and 2.2 kiloohms of resistance. So about 2.27 microseconds. 2.27 microseconds is our time constant there. So I'm going to put that in our equation. And there we go. Now, what is the maximum current we're going to? Well, eventually, we're going to have all the current flowing through the inductor, and the inductor at steady state, L equals a short circuit, okay? So basically, once we get to steady state, this is just a wire here. So our I sub L max will be E over R, which is 12 volts over 2.2K. So that'll be about 5.45 milliamps at max. So that's what goes here in our equation. 5.4 milliamps would be the maximum current through the inductor. Okay, so let's talk about the voltage drop across the inductor. Now it's doing the opposite that the current's doing. As we start out, right as we close the switch here, our inductor is going to look like an open circuit. So it's going to be a maximum voltage at that point, and then when it gets to steady state and it's a short circuit, it's going to have a voltage of 0. So the equation is going to be the opposite equation. It's just going to be e to the minus t over tau. And that maximum voltage is going to be right there at the beginning when our inductor looks like an open circuit. At that point, there'll be no current through the resistor, so no voltage drop there. So we're just going to start at 12 volts and go down to 0 as that inductor allows more current to flow through that circuit. And then the voltage drop across the resistor. As the current starts at 0, the voltage drop across the resistor is also going to be 0. Okay, remember, because if V equals I times R, whenever the current is 0, the voltage drop has to be 0 as well. So it's going to start at 0 and go to a maximum value where it's just going to do exactly what the current does. So 1 minus e to the minus t over tau. And what is that voltage going to start at? Well, what's it going to end up at is actually the question. So again, once we get to the steady state here, our current goes through R. So let me calculate this down here. So the maximum voltage is at steady state, and that's going to be IR max times R, right? So if IR max is 5.45, and our, let me move this down. .45 milliamps, and we have a 2.2 k ohm resistor, then we're going to end up at 12 volts there. Okay, so basically what's happening, we've only got these two we've only got these two components in our circuit. So they're going to kind of divide the voltage as throughout that entire storage phase. So when the voltage across the inductor starts at 12, the voltage across the resistor will be 0 at that point. When the voltage across the resistor is at 12 at the end of this storage phase in steady state, the voltage drop across the inductor will then be 0. And at any point in between, these will add up to at 12 volts. And we'll calculate a few of these and see. So let's just say how long, first of all, how long will the storage phase last? Remember, it's going to take about 5 time constants to get through the storage phase. Okay, so 5 times tau is 5 times 2.27 microseconds. So let's see how long it's going to take. So about 11.35 microseconds. So that's how long it's going to take to get through the whole storage phase. However, in your equation, this is just tau, okay? We don't want the 11.35 microseconds there. We're trying to calculate what's happening throughout this phase. Okay, so let's say we want to find I sub L, V sub L, and V sub R at, let's see, what time? Let's say 5 microseconds, okay? What I would do to calculate that, I sub L at 5 microseconds, I would just put in my equation, 5.45 milliamps, 1 minus e to the minus, now this is where you'll put this. You'll put this right into T, okay? So 5 microseconds over 2.27 microseconds, and then we'll calculate that. Okay, so try plugging that into your calculator. And make sure you don't forget the negative sign there. Okay, so at 5 microseconds, we're all the way up to, let's see, about 4.85 milliamps. Okay, so remember, our current is starting at 0 and climbing to that 5.45 milliamps point. So after a little less than half, it's getting up there. Okay, this is probably at about 2, a little bit more than 2 time constants. So we should be at more than about 80% of our final current. Okay, so let's look at V sub L, also at the 5 microseconds. So I'm just going to grab that equation and plug in the 5 microseconds over 2.27 microseconds. So that voltage should drop down a good bit. It should now be at about 1.33 volts. And then the voltage drop across the resistor at 5 microseconds is going to be 1 minus e to the minus 5 microseconds over 2.27. So there we're at about 10.67 volts. Now notice at 5 microseconds, VL plus VR equals what? 1.33 plus 10.67 is what? That's about 12 volts, okay? So at every point in time, whether it's 5 microseconds, or it's at 0 microseconds, or it's all the way at, 12 microseconds, VL and VR should always add up to that source voltage, okay? They'll be changing during that time, but they should add up at any point in time to that source voltage. That's Kirchhoff's voltage law. It has to be upheld at all points during this storage phase, just as Ohm's law is also accurate at every single point. If you need to, go back over this video and work the problems first, and then look at my answers.